If you haven't picked them up, they were in the front office, we can get them. We have all the homework 35 graded here. Right. So we do have our exam tomorrow. I promised to bring snacks. It'll be hungry. Again, you can bring one page of notes, both sides. That's just whatever makes you happy. It's really, the point here is not to, there will be nothing to memorize on this exam, okay? It's conceptual. All right, anybody have any questions, concerns about the exam you want to discuss? All right, let's continue then. So, what we're talking about right now is time-dependent perturbations. And one of the things that we're interested in the context of a time-dependent perturbation is the transition probability that is driven. We imagine that we have a system that's described by some H0 that describes, for example, the bound states of an atom or a molecule, and then we are applying some typically external field that drives the system, and we're looking for the question of how the system absorbs or emits energy due to this perturbation. Okay, that's the context that we're generally thinking about in this problem. And so the fundamental quantity that we're interested in then is the transition probability, where we imagine we're in some initial, these U's, Ui and Uf, are eigenstates of H0, typically bound states. And we have some kind of evolution operator that's generated by the Hamiltonian, and we're looking at the transition probability to go from the initial state to the final state. And in perturbation theory, we think about that transition probability as, or the transition probability amplitude, the probability is of course the square of the amplitude, as power series in powers of the applied interaction. Okay? And we went to the interaction picture, all that, blah, blah, blah. And at the end of the day, we looked at different situations. So the first order, I mean, to zeroth order, nothing happens if these are different states. To first order, in the interaction, we have this expression. And in particular, we were most interested in this for the context where the applied field was harmonic. That is to say, it was oscillating with some frequency omega of the drive. Okay? And what we found is that this, as long as the drive was on for long enough for many, many periods of oscillation, that the transition probability had this approximate form. And the thing to remember here is that we have the phenomenon of resonance, okay? So when the drive frequency is close to the Bohr energy associated with the energy difference between the two states. So omega Fi here is the energy difference in units of h bar. Then we will absorb energy from the probe resonantly. Okay? And what we saw here is that this term, which we call the positive frequency component, was associated with absorption, when that is to say, situations where the final state has a higher energy than the initial state. Okay, so we're absorbing energy. And this term associated with the negative frequency component is associated with stimulated emission. Okay, because in this case, the energy of the initial state has a higher energy than the energy of the final state. Okay? So that one important takeaway message from here. We have the phenomenon of resonance. We're dominated, the transition probability is dominated by if this drive frequency is close to the energy splitting between two states. That's the dominant effect. Okay? We also studied last lecture situations where the first order contribution vanishes. And we looked at the example, that's a very important example in precision spectroscopy and atomic measurements of fundamental fields. I mean, that's one of the areas of atomic physics, is really trying, for example, people have been looking forever for the permanent electric dipole moment of the electron to look for violations of time reversal symmetry. So the effects of fundamental fields can shift energy levels. And so, for example, the lamp shift that we mentioned ever so briefly, associated with the splitting between the 2p1/2 and the 2s1/2, this lamp shift, which is due to the interaction of the electron with the vacuum fluctuations of the quantized electromagnetic field. One way to try to measure that is to compare this energy, which we see as a microwave energy, with driving this directly here. Now this, we said, this is a vanishing matrix element. There's no dipole moment. In fact, there's no moment of any, and we're going to discuss this a little bit more today, of any moment of the charge distribution that can connect these two directly. So they interact, this just vanishes. So there is no first order contribution, but we can have a second order contribution. And that's what we call two-photon absorption. And that second order contribution, if I'm driving this with a single, say, laser of frequency omega sub L, would be resonant when two times omega L is equal to this Bohr frequency. Okay? I could drive it with two colors, right? And then the sum of those two colors would have to add. So for another example of a two-photon transition that we might consider is here's the, say, F equals 1 of the 1s1/2 ground state of hydrogen, and here's the F equals 0. That's the hyperfine splitting, right? Say for m equals 0, for example. Now there is no direct electric dipole moment that connects these, but I can go up here to the, 2p3/2, for example, with one color, omega 1 and omega 2, detuned by some amount of delta. This is a two-photon transition involving a stimulant, what we call in jargon, this is a stimulated Raman transition. Okay? So it would involve an H plus going up and an H minus going down, for example. Now, what we discussed last time is that this second order contribution could be thought about was discuss in terms of a sum of possible series of virtual transitions. What we would say here is that I virtually excite the 2s, or the 2p3 halves, right? And that's the intermediate state. And then I go back down. And one way that this is often discussed is that I'm allowed to go to excite to that level because I can violate energy conservation. This is a language that is often discussed. For a short time, consistent with the time energy uncertainty principle. Okay? And so I have a virtual excited state here, and the amount by which the probability amplitude to that depends by how much I violate the energy difference, right? So the more violation, the shorter time this exists. As you know, particularly uncomfortable with this language. It's trying to make quantum mechanics sound like things are happening. These are objective, realistic things. That's not the way that we understand the quantum world. That's not the way at least I understand the quantum world. There's an amplitude for this to happen. It's not like something happens in the world and we just don't know it. It's this weird quantum uncertainty thing that we don't even have a language for in our puny human brains to describe, okay? So it's really just coherent dynamics that's going on. Yeah, Stephen?
If you go up from up to 2p3 halves and back down to the 2p1 half, I believe it is.
This guy, these are both in the 1s 1 half.
Okay,
but
so
this is the hyperfine splitting.
Okay, my question is, if you do that case, will one of those H pluses turn to an H minus?
Yeah, that's right. So one of them is associated with absorption. This would be H plus. At that frequency, this would be H minus in that case. Great. Yeah?
I don't know if you already explained this, but so the omega 1 is not quite, H bar omega 1 is not quite the energy difference between.
Correct.
And I don't know if you've explained it, but I mean, is it because the perturbation will blow up if I actually match that exactly?
No, it won't blow up. So the question is, why don't I just do that? Why don't I make it exactly that?
I mean, just
the reason is that if I do that, this has a much higher chance of spontaneously decaying. So if I want to avoid spontaneous emission and I want to have this dominated by the stimulated, then I should detune for resonance.
Okay.
I didn't explain that. All right, if I did, I did it a while ago. All right, excellent. All right, so, right. So now, an important one, as I said, an important takeaway message from what we've studied so far from the point of view of perturbation theory is that when I apply a field that is oscillating at a fixed frequency, that the dominant effect is if the frequency is tuned, if it were the case that the frequency was tuned very close to the splitting between, say, two of the bounds of the system, well, then I could just restrict my attention to those two states. Okay? So when we have a monochromatic or quasi-monochromatic drive with frequency omega close to for some states then the dynamics takes place to excellent approximation in a 2D Hilbert space. Our favorite. What could be better? So what this says is that I don't have, if I have a situation where I have one frequency in the problem, and that applied field is tuned with a frequency that's close to the resonance between two states, and far, far from resonant from everything else, well then, I can treat this problem exactly. I don't have to do perturbation theory. I can just solve time-dependent Schrödinger equation for a two-dimensional Hilbert space. And if this were an atom, this was what we call a two-level atom. Of course, atoms have lots more levels. But when people talk about a two-level atom, what they mean is that we're driving the system close to the resonance between two levels, and then I can ignore all the other levels. They play almost no role whatsoever in what's going on. Okay? So, when we have this situation, we don't have to do no stinking perturbation theory. We could solve the problem nearly exactly. In some cases, actually exactly. All right? So, when we have any kind of 2D Hilbert space, as we know, that's isomorphic to spin 1/2. Okay, mathematically. This isn't spin necessarily. This could be the 1s 1/2 of hydrogen, and this the 2p 3/2 of hydrogen, okay, for some particular sublevels. But I could just map those two states onto they're two orthogonal states. I call one of them spin down, the other one spin up, and I'm done. It's a spin 1/2 particle, voila. And as we know, the only Hamiltonian that governs a spin 1/2 is equivalent to a spin in a magnetic field. So the dynamics is isomorphic to spin 1/2 in a magnetic field. So this problem of absorption or emission when I'm driving a system close to resonance is isomorphic to what we call magnetic spin resonance. And so that's what we're going to start with today. All right, so the picture we have then is the following. We have our two-level system. Let's call this spin up, and this is spin down, for example. No matter what, depends on which direction the magnetic field is, which one's the higher energy, which one's the lower energy. Okay? And let's just simplify the notation a little bit. Let's say that the energy difference between this, the resonance energy, we'll call h bar omega naught. Okay, so omega naught is the energy difference here between the energy of the upstate and the energy of the downstate. Okay? And now we're going to apply to this system a field which is tuned close to resonance, and I'll just call that frequency omega. All right? And it has energy h bar omega per photon. All right? And so we can write down immediately the Hamiltonian for such a system if we wanted So let's imagine the following situation, my spin resonance situation. My Hamiltonian, well, I have my H0, which is what? Well, I can call the zero of energy anywhere I like. Let me call the energy zero halfway in between these, just for convenience. So that this would be equal to h bar omega naught over 2 if I'm up, and minus h bar omega naught over 2 if I'm down. Okay? So that's H0. Right? Yeah.
H naught is always diagonal, right?
Diagonal in what? Everything is always diagonal in some basis.
I mean, it's only on diagonal elements of it.
So we're defining these as the eigenstates of H naught. So by definition, it's that. And then H int is going to be the thing that drives absorption emission. Okay? So it is going to be of that form that's written on the front board with a term that has to do with absorption, right? The H plus term, and a term has to do with emission. So we'll write that as there is a term that takes me from down to up, and that goes like e to the minus I omega t. And then there'll be a term that goes from up to down. And that will go like e to the plus I omega t. And then we need some energy scale here. So h bar, we'll call that frequency capital omega. And just by convention, that we'll understand why we would put it over 2 there. Okay? So this is a Hamiltonian that is of the simplest possible form that describes two-level resonance. We have two levels. They're separated by some energy, which we're calling h bar omega naught. And then we have this drive at omega, which isn't necessarily exactly equal to omega naught. And this drives from up to down and down to up, right? And if we wanted to, and we do often like to write this in terms of the Pauli operators, then this guy we recognize as sigma z, right? And then we have e to the minus I omega t, this is sigma plus, and this is e to the I omega t sigma minus. Yes?
You put it over h bar big omega over 2. Did that arise from the splitting about equals 0 as well?
No, what I said earlier is that's just a convention of how we're going to later interpret capital omega. That factor of 2 comes out of nowhere. It's just a definition that we'll understand why we want to put that 2 in there, because we wanted to have capital omega have a certain property. But it is not motivated in any way at this point. All right, so now how can we understand physically this problem? As we know, we have an almost classical intuition about the dynamics of spins as just rotating vectors that are like gyroscopes. So we should be able to understand this by just thinking about that picture of torquing vectors that are torquing around magnetic fields, right? So let's rewrite this. Remember, sigma plus is sigma x plus I sigma y over 2. And sigma minus is sigma plus minus I sigma y over 2I. Okay, so stand factors of 2 with it there. So So I can rewrite my Hamiltonian in this case as h bar omega over 2 sigma z plus h bar cap omega over 2, and then I have cos omega t sigma x plus sine omega t sigma y. All right. Okay. So how do I interpret this? Well, remember, this is supposed to be equal to minus mu dot b. I mean, everything is of that form. There's no other Hamiltonian in the problem except that, right? So if I rewrite, if I write that, I could write that as, if I write mu as gamma, the gyromagnetic ratio times the spin, or gamma h bar over 2 times sigma, where gamma is the gyromagnetic ratio. And let me take this to be like an electron, just so I can get rid of that damn minus sign, and take I'll take gamma to be negative, as it would be for an electron. Okay. Then my Hamiltonian, right, it's it has this equivalent form if I say that there's a component of the magnetic field in the z direction that is constant, and a component of the magnetic field in the x and y direction, which is oscillating at frequency omega. So what I did in this case is looked at this and said, this is equivalent, my Hamiltonian is equivalent to a spin in a magnetic field where I have my magnetic field has a constant z component and a component in the xy plane that I'm calling has amplitude d perp that is oscillating in this way. So if I assume that, then my h bar omega naught is equal to the Larmor frequency associated with the z component. And my energy associated with the absorption and emission is related to the amplitude of the transverse magnetic field. Right? Everyone see that? So this problem, a spin in this magnetic field, is isomorphic to this problem. They're one and the same. So what is this problem? Well, in this case, what I have a magnetic field in the z direction. That's fixed. It's constant. Right? In time. And then I have this field in the x and y direction that's oscillating. And what is that field doing? It's rotating in a circle. Right? In this case, the way that I've set it up. Now, I'm going to take that to have a much, I don't have to for this problem, but we'll see why. It's not important at the moment, but I'm going to take the amplitude of the rotating field to be much smaller than the amplitude of the z. That's not important at the moment, but we will consider that ultimately. All right? Okay. So that's my magnetic field. This magnetic field is rotating around in the xy plane at some driving frequency omega. All right. Now, what will happen to our spin in the presence of such a time-dependent field? Well, let's just think about this like a classical magnetic moment, a gyroscope under these torques. Okay? If I had my magnetic moment like that, well, in the absence of the driving field, it will just process around this, it'll torque like a gyroscope around that field. And it will long more process at what frequency? It will long more process at a frequency related to the gyromagnetic ratio times that, which is what we call omega naught. So that is what we might call the free oscillation frequency in the absence of the time-dependent drive. Okay? Now we apply this transverse magnetic field that is rotating around that frequency omega. Okay? Now, if this were just a constant field, and there wasn't this field, well, this thing would process around that at frequency, the gyromagnetic ratio times the magnitude of B per, right? But it's not a constant field, it's a rotating field. However, I can go into the frame that is co-rotating with the transverse magnetic field at frequency omega, right? And in the reference frame that is co-rotating with the magnetic field, well, then I have a constant Hamiltonian. I have a constant B field. Right? For example, suppose that I'm right on resonance. Suppose that omega equals omega naught. Okay? Well then, in the co-rotating frame, what does the spin see? It just sees a constant magnetic field. Right? In fact, well, as we'll see in a moment, when I go into the co-rotating frame, there's Larmore's theorem, as we described, you have to subtract out the effect of the standing field. It just sees this guy, and it will just process at that frequency. I mean, you can kind of see that, right? I mean, what's going to happen in the lab frame is that it's rotating around and at the same time processing around this thing. So the whole thing is spinning around actually in this way. Its whole thing is spinning around at omega naught, but now it's processing at frequency right on resonance. In other words, when the rotating field rotates at exactly the frequency omega naught, the effect of the torque around the transverse plane continues to add up. It just constantly is feeling that torque. And it's going to process from up to down and up to down, while at the same time spinning around. So the whole thing is spinning very rapidly at omega naught, and then processing at this, in this case, smaller frequency, capital omega. This is the problem of this is the example of what we call spin resonance.
still in the limit where Z is much greater than B perpendicular?
So that's a good question. None of this depended on that. This would be true regardless of that approximation, okay? In this case, it didn't make a difference that I made that assumption. It's the same dynamics regardless of that being small or big compared to that. Yes.
But to have big omega equal omega naught, wouldn't the B perpendicular field have to have the same amplitude as BZ or no?
No.
Okay.
So there are three frequencies here.
Okay.
Omega naught,
Uh-huh.
omega, little omega, and capital omega. Okay? They're three different things. So what do they represent? Capital omega, omega naught is the precession frequency around the static field. This omega, little omega, is the driving frequency. It's the frequency at which I am oscillating this magnetic field. Then there is capital omega, which is the Larmor precession frequency associated with the amplitude.
Okay.
Right? So if we go back to the quantum picture, you see these three frequencies once again, right? So this frequency has to do something about the interaction strength.
Okay.
It's not the frequency at which I'm oscillating, it depends on the amplitude.
So omega needs to, if you want to be complete on resonance, omega has to have the same frequency as omega naught.
Right, so this is resonance. And this, so this was a point, going back to the question that Stephen raised about whether this was small or big. And this goes back to a point we made right at the beginning when we were discussing perturbation theory. The point of time-dependent perturbation theory is that even if the perturbation strength is absolutely tiny in amplitude compared to the free forces, it can have a profound effect on the dynamics if that tiny force is applied on resonance. We've all seen the picture of the Tacoma Bridge, collapsing, right? A tiny little force can add up when you're on resonance. So this can have this torque can be so slow, even though this guy's, but it's nonetheless can pull it from its precession when it's on resonance or close darn to it.
Can you repeat what big omega stands for again?
Big omega stands for the precession frequency of the spin around the transverse field that is proportional to the amplitude of the applied field. It's related to the torque, the strength of the torque vector that is pointing in the transverse plane. Okay, so if I just had that vector, this precesses around it at that frequency. This is capital omega. And it is known as the Rabi frequency. Not the Rabi frequency, but the Rabi frequency. Okay? Right. So let's see that we see exactly these dynamics from the quantum picture. They're really one and the same. For a spin 1/2, everything can be understood as a torquing vector gyroscope. They're one and the same. So let's do it. How do we do it? Well, we want to solve the time-dependent Schrodinger equation. Okay? So we have what we're going to solve. And of course, this guy, the solution generally is we need to find u. Of course, that's not trivial to do when you have a time-dependent Hamiltonian. You can't just exponentiate the Hamiltonian. In fact, does the Hamiltonian commute with itself at different times? Let's take a look at the Hamiltonian. Does this commute with itself at different times? No. For example, at time t equals 0, I have something that is sigma z plus sigma x. But when omega t is equal to pi over 2, right, then I have it along sigma y. And they don't commute at different times. So I can't just exponentiate the Hamiltonian and integrate it. Now, we went through all this rigmarole for lectures on end about the interaction picture. And we could do that. In this case, going to interaction picture would mean going to a frame. Let me come over here just because it's useful. So, what about the interaction picture? Well, the interaction Hamiltonian in the interaction picture is what you get when you take the free processing spin evolution and put that into the time evolution. Right? That's the interaction picture. And what's U naught in this case? U naught is equal to e to the minus I over h bar h naught t, by definition, right? And h naught is the given by sigma z there, right? Now we recognize that. What is that operator u? It's a rotation operator around the z-axis at frequency omega naught, right? So this corresponds to something which generates a rotation around the z-axis. So this is SU2 rotation around the z-axis by angle omega naught t. Okay? So let's just do that. Let's look at what the interaction Hamiltonian is in the interaction picture. So this would be equal, the interaction Hamiltonian is h bar times the Rabi frequency over 2, e to the minus I omega naught t u naught dagger sigma plus e to the plus I oops, that's not omega naught, that's omega. Sigma minus, right? Plugging in for the definition of the interaction Hamiltonian. So what are these things? Well, the easiest way to do that is to write this again in terms of spin up and spin down. Right? So, this, when this, well, let's write it out. This is e to the plus I omega naught t over 2 sigma z. right? And of course, this is an eigenstate of sigma z with eigenvalue plus 1. This is an eigenstate of sigma z with eigenvalue minus 1. So this becomes e to the plus I omega naught t sigma plus. And then similarly, this will be that. So in the interaction picture, this becomes equal to e to the this difference in frequencies, the difference between the drive and the resonance frequency is I define to be delta. It's known as the detuning. You detune from resonance. How much you might be tuned from resonance. You don't detune to resonance, you tune to resonance. So, okay, that's fine, and we could then try to do the time-ordered integral, but we didn't really get very far. This was good for perturbation theory, right? We did the first integral, and then we got, the sinks and all that when we did that integral. It's the same integral we did earlier. But it doesn't really help us for solving the problem exactly. And the reason is that we still have a time-dependent Hamiltonian. So we'd have to do another time-ordered exponential. So this interaction picture was good for doing perturbation theory, but it's not always the thing to do. Anyone have an idea of, if I wanted to get rid of the time dependence in my interaction picture, what should I have done? Here we went to a frame that was rotating at omega naught.
Shift to the frame.
Which frame?
To one rotating at omega.
Exactly. We should go to the frame that's rotating at omega, not omega naught. And we saw that in the classical picture. When we go to the frame that's rotating at omega, well then the magnetic field is static. So let's go to do a different transformation, and it's what is called going to the rotating frame. Literally. Go to the frame rotating at the frequency, don't trip, of the drive, not at the resonance frequency, the natural resonance frequency. Okay? They might be the same if you're on resonance, but they might not. So I'll define a U rotating frame, which is just like we had before, but now instead of omega naught, it's omega. Okay? And now my interaction Hamiltonian in the rotating frame, I'll just call it HRF. No, not going to call it that. For reasons that we're going to call it clear in a moment. Now, deal with my time dependence. So let's just look at this. Okay. It's the same thing we just did, but now omega naught equals omega, right? And this thing is now static. In fact, what it's equal to in this frame is sigma x.
Does the 2 cancel?
No, it stays, right, because these guys, because it was. Right, and we kind of saw that again. I mean, if I started my magnetic field along the x direction, then in my local frame, it's always in my x direction. Okay? So now we need to, of course, if we're going to do this transformation, we have to do the state in the rotating frame. I need to take out that rotation from the state in the Schrodinger picture, just like we did in the interaction picture, but now instead of U naught, it's U rotating frame. And my state evolves in the following way. I have that's the Schrodinger picture state plus that, right? This is the total Hamiltonian times minus I over H bar. That's the Schrodinger equation. And this, according to the definition of what we have over there, here it is equal to plus I omega naught, omega sigma z over 2. Okay, and so now what I'm going to do is I'm going to stick in a URF dagger, and the same thing over here. And what do I have? Okay, what I have is not enough trouble. I see that the time evolution of the state in the rotating frame is equal to URF dagger H URF minus I over H bar minus H bar omega over 2 sigma z URF dagger. Using the fact that sigma z commutes with the rotation around the z-axis. So this is my effect. This is what I want to call HRF. It's the effective Hamiltonian in the rotating frame. What is this? Now, you see, this was an example of what we call Longmore's theorem. Longmore's theorem says that going to the rotating frame is equivalent to adding an additional magnetic field to a problem. Okay? So, well, this is like having a magnetic field with thumbs and subtracting a magnetic field along the z-axis. That's why in that back board, I got rid of, when I went to resonance, the magnetic field along the z-axis. Yes, Stephen?
Is that Hamiltonian in HRF? Is that H naught plus
The
H
whole
naught?
H.
Okay.
So let's write it down. So HRF, the effective Hamiltonian here, is this. Well, that was H bar omega naught over 2 sigma z plus H bar times the Rabi, which over 2 sigma x. Okay, so that's this. Minus H bar omega sigma z. We go to the rotating frame. So this is equal to minus H bar delta over 2 sigma z plus so what we've learned is that in the rotating frame, my spin sees an effective magnetic field. It sees an effective magnetic field along the z-axis that's related to the detuning, and an effective magnetic field along the x-axis that is proportional to the Rabi frequency. Okay. Well, let's first look at this problem exactly on resonance. Yes?
So maybe I'm wasting time here in just like a math, but when you derive the URF in time, why didn't the URF survive? Is that just something I should just figure out on my own, or?
Where?
Like, okay, so you differentiate,
Here,
yeah.
this guy.
I'm sorry, no, the next term?
Oh, this guy?
Should be
when-
there, yeah.
Yeah, there's a du dagger RF over dt, and then you pull the 9 omega sigma z over 2.
Oh, yeah.
But I mean, should there still be a
You don't need the resolution.
I don't need it here. Okay, thanks. Yeah, that should be a URF dagger, right? When I take the derivative of that. So the derivative.
Oh, okay.
Yeah, I screwed that up. Yeah. So that's what happened. Okay, but modulo those details, this is the key point. Okay? That in the rotating frame, what we see is that we have the equivalent of a spin moving that's torquing around these axes. It's got a torque around the x-axis proportional to the Rabi frequency and a torque around the z-axis proportional to the detuning. So, right on resonance, my HRF is just this, right? Now, generally speaking, in the rotating frame then, the time evolution operator is equal to this. Right? That is to say, this is the solution to the Schrodinger equation given that generated by that Hamiltonian. Okay. And that's just equal, no, not over 2, that should be over h bar, is equal to minus I omega sigma x t over 2. So that is a rotation operator around the x-axis by angle capital omega times t. And we know how to write that for spin 1/2. There's the well-known formula. Right? Everyone knows that. And so my state, let's say at time t equals 0, will spin down. Okay? In that picture, I'm in the ground state. And so now it's also the state in the trivial picture at time t equals 0. So the state at a later time in the rotating frame is equal to the time evolution operator which is equal to cosine omega t over 2 down minus I sine omega t over 2. And what is sigma x acting on spin down?
Spin up.
Spin up, right? Because sigma x is sigma plus plus sigma minus. Sigma minus annihilates sigma plus. Okay? So, what is the spin doing? The spin is processing around the x-axis. Okay? So, if, say, this is the z-axis, this is the x-axis, and this is the y-axis, it is processing around the x-axis at frequency, the Rabi frequency, capital omega. That is to say, I start the system spin down, and then over time, it goes to spin up. And then it goes back to spin down. It just processes. This is the state at time t equals 0, and at time t equals 2 pi over the Rabi frequency. I mean, sorry, pi over the Rabi frequency. Yeah, 2 pi, yeah. Right? Etc. When the time is pi over 2, I'm spin up. Right? I'm sorry, not pi over 2, pi. I'm getting this backwards. I'm sorry. When this time is pi, then this is pi over 2. When I go from spin down to spin up, this is what's known as a pi pulse. A pi pulse is applying this magnetic interaction for a time such that omega t is pi, where omega is gamma and the transverse field. What happens if I apply it for a time that's a pi over 2 pulse?
Half pi pulse.
That's a half a pi pulse, and what state am I in at that time?
Nothing figured? Oh, wait.
So now if t is equal to pi over 2, if omega t is pi over 2, then this is pi over 4, and this is pi over 4. So what is that?
Superposition.
It's a superposition with 1 over root 2, right? So this, when I'm at pi over 2, it's 1 over root 2 down minus I up. Of course, up to an overall phase that I really don't care about, that's up plus I down. Right? And that state is what?
Up along Y.
That's up along y. Yes, Stephen.
Because we're on resonance, we're confined to the two-dimensional YZ plane, right?
That's correct. That is correct. So this is an example of what we would call coherent driving. If I want to create a superposition of spin down and spin up, I can do that by applying on resonance with a well-defined frequency, exactly on resonance such that I go from here to here. And then I'm in an equal superposition. Of course, if I continue, then I'm already here. If I continue, I'll drive it back down, and I'll just keep going. And in this case, what we would see is the population in the excited state oscillates. It oscillates at the Rabi frequency. So my transition probability, in this case, to go from down to up as a function of time, what is that?
Sine squared.
Exactly. Right? Which is equal to 1 minus cos omega t over 2. So that probability as a function of time oscillates at the Rabi frequency. And then, of course, halfway in between, I'm in superposition. These are known as Rabi oscillations. Now, this is not at all like Fermi's golden rule. I mean, there's no rate. We'll come back to that next lecture. What happens now to when I'm off resonance?
If you off resonance, couldn't you just define a new plane to be vector dimensional?
Let's see.
Oh, cool.
So let's see what happens when I'm off resonance. Well, there's my Hamiltonian, right? So my time evolution operator now is e to the minus I over 2 minus delta sigma z plus omega sigma x times t.
Should that be H, not 2?
What's that?
Should that be I over H bar?
The h bars cancel over here.
Is there?
So,
A T.
the t is here, I can't see it.
It's fine.
That might be a bad angle too.
Yeah. Right? So, what is that? I mean, so let's look again at my block sphere. Okay. So what do I have? This guy represents, this Hamiltonian, my HRF, was related to something I'm going to call omega tilde dot sigma, where omega tilde has a component along the z-axis and a component along the x-axis. So it is torquing around this vector with a frequency that is the magnitude of that. This is known as the effective Rabi frequency. Let's, for example, look at the case, well, it doesn't matter. So let's say delta was greater than 0. Say it was between the upper residence. Well, then what do I have? I have this vector, and then so my torque vector is like that. It has a component that is delta along this direction, and then it has a component which is the bare Rabi frequency along this direction. If I start the system spin down, it will precess around this guy at that frequency. Okay? Shouldn't go out of the sphere. Okay. So it precesses around this axis. Now, you notice it never has 100% probability to be spin up. It has some probability, but never is 100% probability to be spin up if I'm off resonance. So let's solve that problem. Let's solve it. What is this? We can rewrite this as e to the minus I over 2 to the effective Rabi frequency times time times something I'm going to call sigma n. Sigma n is the Pauli matrix in the direction of this. So this vector has a magnitude and a direction. What is that direction? That direction is the vector over its magnitude, which is minus delta over the effective Rabi frequency in the z direction plus the bare Rabi frequency over the effective Rabi frequency in the x direction. Okay? So we can now solve this problem. My time evolution operator, thus, is equal to cosine the effective Rabi frequency over 2 times t times the identity minus I sigma n sine the effective Rabi frequency over 2t. So now I ask you, what is the transition probability to go from down to up as a function of time? Well, that's equal to the right? And that this term does not contribute, but this term does. So that's equal to sigma n sine squared right? So what is this? Well, sigma n is sigma dotted into this, right? There's sigma n. This first term contributes to nothing. It's all this guy. Right? So, this term is this. I'll leave that to you. Times that.
And unless delta equals to 0 is never equal to 1.
Then it's 1. Then we're back where we were. So let's just conclude with what we found. Let's come back to the front board. So this is what we have for delta equals 0. More generally, what we have is this transition probability is equal to omega squared divided by sine squared, the square root of omega squared plus delta squared over 2t. So, this is for delta general. It could. So when delta is not equal to 0, doesn't matter whether it's positive or negative, this is the same. What we see is two things. Firstly, it oscillates at a faster frequency. And secondly, it doesn't get all the way up to unity. We see something that looks like this. And that is the picture of what's happening here. The more I'm detuned from resonance, if I'm detuned very far from resonance, then I barely get out of the ground state. And I oscillate much, much, much more quickly. Okay? All right, we will continue this next time. And then say, well, what about Fermi's golden rule? I don't know, what does that have to do with this? I know that's what you're thinking. So, all right.